It's a pleasure today to have Ira Shokar talk to us. Ira is just next door, as a PhD student in DMTP. He's going to tell us about beta-plane jets. Please, Ira.
Thank you, everyone. Hi, I'm Ira. This is work that I've been doing in my PhD alongside Peter Haynes and Rich Kurzweil at the Department of Maths, and I'm also part of the AI for Environmental Risks CDT. And today I'm going to give a talk about how we can use data-driven approaches to try and learn and model systems, geophysical systems, and in particular the dynamics of beta-plane zonal jets. So to motivate this talk and the work I've been doing is that, as we all know here, simulations in GFD, we often have to make compromises when resolving scales. We'd love to be able to model every relevant scale, but we have to make compromises. And often these parameterizations that we use lead to model error or other kind of biases in the models that we have. So we want to try and find some way to bring in these parameterizations that we're making. And often these parameterizations in global circulation models are stochastic. They want to account for the uncertainty and the chaotic behavior of the system by looking to model ensemble as opposed to modeling a particular realization. And that kind of motivates why we're going to be looking at a stochastically driven system here. And on the right here, we've got a diagram of the kind of the model resolution determined by spatial scale and temporal scale, and the kind of dynamics that can be resolved. And the dotted lines, the one on the left is the single forecast that ECMWF produces. The one on the right is the ensemble forecast, and then for the two vertical lines, the upper one is the ensemble forecast, and the lower one is the single forecast. And we can see that when modeling global climate models or global circulation models, processes like convection and turbulence are often, maybe if we use a laser pointer actually, processes such as convection and turbulence are often missed, and we know these are important processes for modeling system science. And what we're going to be looking at here is the jet stream, or modeling zonal jets, and the jet stream obviously exhibits large variability and often drives European weather, which is kind of the motivation as to why we're interested in it. And to study jets, we're going to look at a very idealized system. Laura gave a fantastic talk a couple of weeks ago outlining all of this. I'm sure everyone remembers, but I'll give you a little introduction. So we're going to be looking at a doubly periodic system in 2D, where the turbulence or the eddies are being parameterized by a stochastic forcing, which is homogeneous and isotropic, and we force in a certain wave number in Fourier space. In this case, it happens to be 16. I'll talk about the parameters that we use. And then numerically, we can solve the vorticity equation that we see up here. And then on the right, you see a snapshot of a vorticity field with the potential vorticity plotted in black here. Often we look to do some sort of coarse graining or some averaging process. Here we use a Reynolds decomposition where we sort of want to separate the large-scale dynamics from our fluctuation fields, and we do that by means of a zonal averaging process. One could look at different averaging processes like filtering or other coarse graining. And by doing that, we obtain an evolution for the mean equation, which we see here, and then we have the fluctuations here. And why are we going to do this when it comes to looking to model this system? Well, there's kind of two reasons why we do this, and one, both to make it simpler and to make it more difficult. We wanted to make it simpler so that we bottled our system down to a 1D dynamics, and when it came to doing any kind of machine learning, it was easier to do anything in 1D before moving on to 2D or 3D, but also make it more difficult because now if we're looking to model the mean flow equation, we don't have any information of the fluctuations. That makes it more difficult for the machine learning model, and it has to parameterize those fluctuations in some way, which I'll get on to. And when we plot latitude time diagrams of the mean flow, these are different ensembles as again, we're forcing the system stochastically. So for any realization of our forcing, we see, the colors are a bit off there, but that's fine. We see different realizations of our system where we have this dotted line that you can see here. Up to there, the initial conditions are identical, and then from that dotted line, we have the system evolves under different realizations of that forcing noise, and we can see that the subsequent dynamics start off very similar and then diverge into different dynamical regimes. And yeah, as I say, that gives rise to lots of complex phenomena of interest. These include these coalescence events where two jets come together. We have latitudinal translation where the jets move in the y direction, and we see the nucleation of new jets that seems to be almost completely spontaneous. And the questions that we want to ask are, can we use deep learning to emulate the time-evolving systems of the dynamic? As I said, just looking at the mean flow equations and without any knowledge of the forcing form or the interactions between the eddies and the mean flow. And then the other question we want to ask is, if we can build an emulator that's very, very fast, what can that tell us about how these events are driven? Are they deterministic? Are they completely captured by the mean flow? Or are they stochastic? And is that eddy mean interaction important? And also, I must say, if anyone wants to jump in, this is all sort of work that's being done at the moment. If anyone wants to jump in and ask questions and say anything at any point, please feel free. So I'll kind of motivate how we kind of built out the machine learning system. While it wasn't strictly necessary to look to reduce the number of degrees of freedom, as I said, we were already using an averaging process. And in our simulations, we looked at a resolution of 256. So we didn't need to do this step. But to build out this kind of, if we wanted to then look at 2 and 3D dynamics, just to reduce the degrees of freedom, we're going to look to project our system onto some latent dimension, evolve the system in that latent dimension, and then project back to physical space. And we do this in the form of what's known as an autoencoder process system. So we take in our dynamics, we give some sort of time history of the system to our machine learning model. We map down to some latent space using an encoder. We then process the system in this latent space, which is of a smaller number of degrees of freedom. And this must be stochastic to represent the system that we're trying to model. So we also send in some noise. And the machine learning model has to learn how to take this noise and appropriately weight it given the system, given the state of the system that we have. This can then happen autoaggressively in the latent space. So we can take the outputs of our machine learning model, put it back in to get a new forecast, and at the end we can decode out the outputs. And I'll get on to what each of these components mean in a second. And firstly, we did this for a particular set of parameters. So these are a set of parameters in our equation, beta 0.9, mu, and epsilon, the forcing amplitude. And this was all done for, I didn't write it up here, but this is for the forcing wave number was k is equal to 16. And to tell our machine learning model how it's doing well and what it should be learning, we have to impose what's known as a loss function or objective function. And the loss function that we used is called the continuous rank probability score. This is, if anyone is a sort of meteorologist, they're aware that this is often used as a metric in meteorology to kind of indicate how skillful a forecast is for an ensemble. And essentially it takes 2 parts. It's an extension of the mean absolute error where we have, every time we produce an ensemble forecast, so this is what this I denotes here, we then measure the difference between each of our ensemble members with our truth realization here to try and get each of our ensemble members to be close to the truth. That's our objective. But also we want to encourage diversity within our output. So each of the ensemble members here, we take the difference between each ensemble member to the next. And this minus sign, as we're looking to minimize the CRPS, means that we're trying to maximize this ensemble variation. And these are weighted appropriately so that the skill, or the mean absolute error, and the spread, the ensemble variation, are to be almost equivalent. So we have a skill spread score of 1, which in meteorology or in probabilistic forecasting is seen as a good forecast. So I'll talk a little bit. I won't go into too much detail about the architecture. If anyone is interested, then they can ask me more. But this is the autoencoder structure. So we take in a snapshot of our system. We put it through these convolution layers with the nonlinearity. So these are learning a nonlinear mapping down to a latent space. And then we have a sort of a mirroring architecture that takes our latent space and produces it back out to our physical space. And the only difference between these convolutions, and if anyone has ever used a convolutional neural network, is that what these layers do is they look to do the convolution in the form of a complex linear multiplication. So in a convolutional neural network, one passes a kernel as a patch over an image as a sort of local receptive field, and then uses pooling layers to make that receptive field larger, and that allows the model to attend to different scales, often used in images. But this, by just applying a global weighting function in Fourier space, means that we can do local and global attention, or look at local and global scales at the same time. And that just meant that we only needed 2 layers as opposed to these very, very long and deep networks that are often used in image processing. And again, to tell our model how well it's done and to give it an objective, we use the mean absolute error between our forecast output, or not our forecast, but our output of our encoder-decoder model and the truth value. So this is essentially trying to model itself. It takes in an image and it tries to produce a snapshot or an image that's as close to that initial image, but it's gone through this bottleneck. So the number of degrees of freedom that are in this bottleneck reduce the expressivity of the model. And then also we found that when it comes to these order reduction models, these models often like to cheat. And that is that they're happy to represent the large scales, but they often don't care about the small scales, because the energy in the higher wave numbers is reduced compared to in the lower wave numbers. So if it's trying to make some sort of dimensionality reduction by using a reduced number of latent variables, it will often represent the large scale features and misrepresent the small scale features. So we add in a second term here, which is a mean absolute error of the modulus of the Fourier components. And that penalizes any reconstructions that try and misrepresent or fail to capture the high frequencies. And we'll look at some energy spectra later to see how that does. And then again, this is a bit hairy, so I'll go into the details, but this is the kind of time-stepping algorithm we use, and it's called a transformer. And the transformer is the T in GPT, for anyone who's been looking at the evolution of language models recently. And essentially, they're very good sequence modeling architectures, where they take in, here we take in our history of latent variables, we append a noise vector, and we go through a number of different layers to take these and try and give a prediction of the next time step, the same way that a GPT model is trying to predict what the next word could be, having seen a sentence or some sort of prompt. And the difference between this and other neural network architectures is there's a multi-headed attention block here, which again, one doesn't need to worry too much about. But essentially what we do is we have our latent variables here, we add in our noise, each of these is then sent through a linear transformation where we get these 3 vectors. We then look at a similarity between 2 of the vectors that have gone through this linear transformation, and we have this dotted line, which I guess is the difference between the standard transformer and what we're doing here, where this dotted line, to the right of this dotted line, is a standard transformer where it looks at temporal correlations in our latent history to give us to look at, as I said, to model the temporal histories and give us how the temporal output would be. And then the right-hand side of this, I guess this addition, is the weighting function between the temporal histories and our input noise here, which essentially is the model determining how important is this noise vector and how much should we weight it given the system state that we're in, i.e. the latent variables that it sees here. And then to build out the loss function for the entire model, we have these kind of 4 parts. One is that CRPS that I talked about when it's trying to make a prediction, T+1 of the next time step against a truth. And as I said, at each time we predict an ensemble. That ensemble was reasonably modest. It was a size of 8 against a single truth trajectory. Our mean absolute error for our encoder-decoder part, our Fourier absolute error, and then this additional CRPS loss, which is to enforce, we have a nonlinear mapping here, a nonlinear mapping that is not necessarily space preserving, i.e. distances in physical space are not necessarily close in latent space. So we add an additional term here which penalizes the latent space and tells our model that if we have a distance in physical space that's close together, it should also be close together in latent space. And that helps both with modeling, but also later if we want to do any interpretability of our latent space, it helps that if 2 points are close in latent space, then it means that they should be close in our physical space. So that's the kind of machine learning part of it. Now we can look at results and interpret this and look at kind of what the physics has learned. Often in learning of physical systems, one will take a realization from a numerics, take a realization from the neural network, look at it over some short period of time, look at how close they match, look at the mean squared error or some sort of metric like that, and say we've done really well, our errors match very close. But of course we're looking at a stochastic system here, so that doesn't make much sense to look at a single realization and a single output of our machine learning model. So what we instead want to do is look at comparing ensembles. And again, we have this dotted line here. Beyond this dotted line, we have different realizations of the system under force noise. And then we can look at how the machine learning model does, where it's given these initial conditions up to the dotted line, and then just under different sampling of that forcing vector that we give to our machine learning model, we see that it produces dynamics that we kind of expect, where over short periods of time, this merging event becomes apparent. And then beyond that, we see that the kind of expected latitudinal drifting, we see merging events that we'd expect to see here, and we see the nucleation of new jets that we'd expect. And we can quantify this. We can look at the short time evolution by looking at the CRPS, which, as I said, is used as a metric to look at probabilistic forecasts. So now we can use this, what we used as a loss function, now as a metric to look at how well our model has done. And what we can do is we can plot the 2 components of this mean absolute error, and this is ensemble variation with the mean absolute error on the top, the ensemble variation on the bottom. And what we do is we pick a particular trajectory, doesn't matter which one, we pick the first one here as our reference trajectory, and then we evaluate the CRPS for the numerical ensemble, where the other 7 trajectories are used as the ensemble members with respect to this, and then we can calculate our CRPS, and that's what we see in the green. And then we can also do the same for the neural network, looking at this ensemble, comparing it to this particular trajectory, and plot that in red, and we can see that the sort of magnitude of the CRPS loss is comparable between the ensemble generated by numerics and the ensemble generated by our machine learning model. And then for comparison, we also used a VAE. This is called a variational autoencoder, where instead of using the CRPS loss as our objective, we instead use what's known as the evidence lower bound as a loss function. And we saw that using that particular loss function just didn't give us the results that we saw with this CRPS-based loss. We then, if we want some sort of emulator, want to look at how does it perform for very, very long time evolution. Does our model go off into some unknown regime that we wouldn't expect, giving us unphysical results? So on the top, we can see a sort of very long 20,000 time step evolution of our numerical integration. And then we can do the same and look at the output of our machine learning model, the sort of transformer-based model. And then also compare again to that VAE-based model, where we can see that the model, the errors that we saw on the previous slide, which were much larger initially, grow and grow and grow, and we fall into these unphysical regimes. And there was one other architecture that we wanted to compare against, which is called the adversarial neural network, where we have 2 neural networks, one that's generating the outputs and one that's a classifier that's trying to determine how good the outputs are that's generated by the neural network model. And the neural network model tries to trick or tries to overcome the classifier model to the point where the classifier cannot distinguish between what's being generated by a machine learning model and by the input numerics that it's seen. And initially, these also look good. It doesn't seem to fall into these unphysical regimes. But then when we looked closer, we saw that the model was doing something really strange, where it learned how to trick the classifier and give us some sort of dynamics, i.e. this set of dynamics where we see this latitudinal drift, we see this nucleation and this merging event, and it learned that if it just repeated that, it was able to trick the other classifier model. It doesn't give us something very physically realistic, but gives us something realistic enough that tricks the classifier that falls into this pitfall that we didn't expect. That the CRPS-based model that we used up here didn't seem to fall into that kind of pitfall. And again, we can quantify these using some sort of quantitative measures, and what we do is we look at the PDFs over these very long time histories of the PDF of the values of u, and then we can look at the first derivative in y and the first derivative in t to give us some representation of the spatial and temporal correlations. And we can see that the ML model and the numerics match up well. And we can go ahead and plot these as sort of joint PDFs between, on the x for all of these plots is the values of u. The top two plots show that first derivative in y, and the bottom two plots show the first derivative in t, with these two in the green box representing our numerical integration, and these in our red box representing our machine learning model. And again, we can see that they look very similar, and we can use something like the KL divergence or the Hellinger distance to get some sort of quantitative measure as to how these compare. And then we can look at some statistics that we're interested in. So these are the PDFs of the number of jets and their transition rates, where on the x-axis we have the number of jets. In green, we have if within a time window of 10 time steps, we didn't see a transition to a new number of jets, then it was characterized in green. If we did see a transition where we increased the number of jets, that was plotted in red. And if we saw the number of jets decreased, that was in blue, with the solid lines being shown for the numerical integration and the dashed lines being shown for the ML emulation. And again, they match up well to kind of verify that the model is doing as we expect. And as I talked about before, we can look at the power spectra in wave numbers and see that the ML model, thanks to that additional loss term, is able to recover both the low frequencies that we expect it to get to be good at producing, but also these higher frequency wave numbers. It's able to reproduce those, which are important. Without that loss function, maybe I should have plotted it, but we saw a drop off essentially here, where it wasn't able to reproduce these higher wave numbers because it was essentially learning that it could just reproduce these lower wave numbers and give us outputs that looked physically realistic, but wouldn't actually measure up. So what we did is we learned how to emulate a model for a particular value of beta, which is one of our key parameters. This is another plot from Laura's thesis, where we have two key parameters. We have the zonal parameter, and we have the Rhine's wave number. And we can here plot a phase-space diagram with the number of jets that we see under in these different parameter regimes. And I guess up here is how those are determined based on the key parameters in our system. And if we want a true emulator of the system, then we want something that is able to not just learn a particular value of one set of these parameters, but learn to be able to generalize to a number of them. So first of all, we essentially picked one parameter, that was beta, that we're going to vary. This again from Laura's thesis is if we take a value of beta and increase that over time, we see that we have these different kind of dynamical regimes, where we start off in this frictional regime, we end up in this kind of high zonostrophy regime, and we have this kind of transitional regime in the middle. And just by varying this one parameter beta, we get this kind of range of dynamics. And we wanted to see, could we take this machine learning model that we used and generalize it to a range of parameters. We chose a single parameter first because it just made the sort of phase space of training much easier. But one thing we're wanting to do now is look at how do we vary a multitude of these parameters. And how do we adapt our model for this? Well, it ended up being reasonably simple. We essentially just inform our model what the value of beta is for the sort of time histories that we give, and that goes into this attention model as just an additional variable that's added to our latent histories that then goes into our these learnable parameters then see, and that informs the ML model which regime of beta it should be producing outputs for. So we can again look at ensembles, and here look at a range of values of beta, starting with beta 0.3, 0.6, 0.9, 0.8 for given values of mu, epsilon. And our initial training that we saw previously showed our machine learning model 200,000 time units with beta was equal to 0.9. And now we're going to take those model weights and fine tune them. So do an additional training process with a discrete number of values of beta, showing just 5,000 time units. And maybe what I should have said is that initial training with 200,000 time units took about 4 hours trained on a GPU. And then this additional fine-tuning then takes about 30 minutes on a GPU. So the training time wasn't enormous. And again, that's because I suppose we're only looking at a 1D system with 256 degrees of freedom. Now that we're looking at 2D and 3D, the 3D snapshots, that training time does increase. And so we can then look at how the ML model does in emulating the system given initial conditions before each of these dotted lines, how it then performs. So we generate an ensemble for each of these values of beta that it had seen during training, during this fine-tuning process. And again, we can see that it gives us the kind of dynamics that we expect in this kind of low beta regime. We see a single jet. We see this kind of sharp latitudinal translation. Beta was 0.9, which wasn't shown during training, but was just to make sure that it hadn't forgotten what beta 0.9 had looked like in this kind of transitional regime. And then we move towards higher zonal. And the machine learning model, again, seems to produce dynamics that we'd expect. And then what we wanted to see is, given that it was trained on this set of parameters, how would it do when interpolating between these values that it had seen during training? So these are then values that it hadn't seen during training, but were within the bounds of the training set that it's seen. And again, we have at the top here for each of these values of beta, 3 numerical integrations, again, kind of a single or 2 jets down here, moving up to high zonostrophy. And again, we see that it reproduces dynamics that we'd expect, despite not seeing any of these examples during training. And we can again quantify how well our model does. So we take these long time histories, and we again look at the contribution or the joint PDF, again on the x-axis between the values of u, our zonal velocity, and then on the y-axis. So for here, we have the first derivative in y, the first derivative in y for our ML model, first derivative in t, and derivative in t for our ML model. And again, we can see that for the different values of beta, except maybe for this high value of beta where these 2 plots don't quite match up as well, we generally see very good matching between the PDFs of the numerics and the ML emulation. And we can again look at the energy spectra to see if the model was able to reproduce the dynamics at all scales as expected. And we, for each of these values of beta, and again, it sees that it matches up. It doesn't kind of fall flat on its face in any kind of particular part of wave number space. So we now have this emulator that we can trust reasonably well, having looked at those kind of statistics. What can it tell us about the system, and what can it tell us about the dynamics that we might not have been able to do before by just using the kind of traditional numerical integration? So here we have a reference coalescence event that we see here, and the x-axis is time with respect to that. So a 0, we move 0 to where that event is, and then we go back. This is 10, 20, 50, 150, and 250 time steps. And we initialize an ensemble given at these different initial conditions, and we measure when do we see that a nucleation event takes place. Sorry, a coalescence event, the merging of 2 jets takes place. So here at the top is that PDF when 250 time steps away, and then down at the bottom is when we're 10 time steps away, with again 0 being with respect to that reference event. And what we can see is that this is a reasonably deterministic process. Even when 250 time steps away, there's a large amount, the probability density that's kind of expected that in 250 time steps we will see a coalescence event, and then as we move closer and closer, that becomes closer and closer to a sort of a delta function. And on here we can we've plotted two things. We plotted in green for a numerical integration, so this is an ensemble of numerical integrations, and in green is showing us an ensemble generated by the ML emulator. And on the right, I just wanted to highlight the kind of difference in time and how long that took. So the numerical integration, which was written on Julia to run on GPU, reasonably performant code, took about 10 days to produce the PDF for one of these plots, and the deep learning model took 43 seconds. It's very fast, which means in these plots we show 1,000, an ensemble size of 1,000 for the numerical integrations, and we show it for 1,000,000 for the deep learning model, which one wouldn't be able to do with kind of traditional numerics just because of the kind of speed. And this is because most of the compute is offloaded to training during deep learning, which makes the inference time very, very fast. And then we can look at a nucleation event where we pick out this reference nucleation event. Again, the colors don't show up too well. Hopefully you can see that all right. But there's a nucleation event up here, which we mark at time t equals 0. And then we go back in time and set off ensembles at different initial conditions. And what I must say also is this was for beta 0.9, so this was one of the ones that it's seen during training. And then after, I'll show you an example that I haven't seen during training. But we can see the dynamics are kind of very different, where here, when 200 or even 50 time steps away, I'll highlight that just now, the system is much more, or what we'd call stochastic. The likelihood, or the most likely time for a nucleation event is almost immediately after the initial conditions. And it's not until we get very, very close to the event that we see something where we move towards this kind of Gaussian, or even closer towards a delta function where something more predictable. And this is kind of confirming also what Laura saw in her thesis, that the coalescence events are sort of much more deterministically driven, while the nucleation events are much more stochastically driven by that forcing or that eddy mean interaction. And then we can look, we've seen that our model did well for a value of beta that it's seen during training, but what about for a value of beta that it hadn't seen during training? This is about 0.135. And again, we pick out a reference coalescence event and a reference nucleation event, and we look at when we are 25 time steps away, so this is for C and G, and when we're 100 time steps prior to that event, B and C. And again, we see that same dynamics, and we also see, crucially, that the ML model is showing us that the PDF is matching very well to what we see in the numerics, where the nucleation events are much more stochastically driven than the coalescence events. And now that we have this emulator, one could pick out any other event that they saw during training or in different values of beta, and very, very quickly produce these PDFs with reasonably, hopefully, good trust that the PDF that they'd see is what they'd expect to see in the numerics, but it would take them a matter of minutes as opposed to a matter of days or weeks to produce these PDFs and study any other part of the system that they might be interested in. So that kind of concludes my talks. The kind of the two questions we had is, can deep learning emulate the time-evolving dynamics of a given system without any knowledge of the forcing form and the interaction term? And that's yes, we saw that it was able to do that. And then the other question we wanted to sort of understand by building this system and then looking at the ensembles is to what extent are these events that we see deterministic or stochastic? And we showed that the nucleation events were highly unpredictable and driven by the stochastic forcing and the eddy mean interaction, while the coalescence events were much more deterministic. And the kind of work that is now going on for the kind of remainder of my PhD is we looked at valuing just a particular value, one of these parameters, beta, but we want to ideally produce the kind of full state space of possibilities for the system and maybe replicate something similar to this if we were able to value also mu, epsilon, and the forcing wave number. As I said, we were looking at essentially modeling a 1D system that was, or a 2D system that was stochastically forced, and then reducing this down to a 1D system. But what if we look at a multi-layer system? So this is multiple layers in Z that generates its own turbulence. And if we were to only pick out, say, the top layer without any information at the bottom layer, if we were to coarse grain it in this way, would the ML model still be able to parameterize the vertical interactions, or if we were to do any coarse graining, parameterize the small scales without any knowledge of these, but using a probabilistic approach? And then finally, with some collaboration with Matt Chantry at ECMWF, we're looking to apply this to WeatherBench. So this is a benchmarking data set looking at short and medium range weather forecasting. And would this kind of probabilistic approach do well to forecasting medium and short-term weather? So on that, I just want to again thank Peter and Rich and EPSRC for funding my work. The work has been written up into 2 papers, one that's available as a preprint now and one that's under review at an ICLR workshop, and will be available in a week's time or so. So if anyone has any questions, I'd be happy to take them. Thank you.
Very nice. Questions?
You showed the different behavior between nucleation and coalescence while interpolating within your parameter range. Have you played the game of trying to have your network as it is trained, and having not been trained on a specific type of stochastic forcing, then run the DNS with that type of stochastic forcing, and how would you compare?
So that's not something we've tried. I guess most everything, and I guess with a lot of data-driven approaches, it's often quite not dangerous, but you wouldn't expect the model to be able to do anything that it hadn't seen in training. So everything that we've done is, as you said, with a particular prescription of the forcing and a particular prescription of the parameter state, except for beta, where we have these bounds that we're happy to look within but not out of. It might be interesting to see what the model would do if it was shown a different prescription of the forcing or something like that, but it's not something that we've tried just because, as I said, it's quite dangerous to try and extrapolate in any kind of way, given that it hasn't seen any information of that.
Presumably that's really where you'd like to go, though, isn't it? I mean, you've got a Reynolds number, have you? Or something.
Well, in effect, you're non-dimensionalized, but yes.
So again, you might say, what if I went? And what you'd like, isn't it? You'd like to say, I can do something with this that I can't do.
Yeah.
And so you say, well, I'll go to high Reynolds.
Sure, but I think what's more realistic is that it only requires a much shorter amount of kind of new data to train, to almost not retrain, but add in any additional ability to the model. So I think what's more realistic is if it took you a very long time to get a DNS at a very high Reynolds number, you'd be able to use a reasonably reduced training data set to then add to your model that it would then be able to understand what that high Reynolds number would do, as opposed to just expecting it to be able to look at that high Reynolds number, not having seen anything in the dynamics. These are very nonlinear systems. We know that the dynamics don't extrapolate in a very obvious way. But what I think, as I said, what I think it does show is that one can train on a region that might be very easy to produce, i.e. here we just have beta as 0.9. All of these are equally easy, but in the example of Reynolds number, we could train the bulk of our model on a regime that's reasonably easy to produce data for, and then fine-tune on regions that are more difficult to produce large amounts of data and generalize the network that way. Yeah. There's one over there.
So,
Yeah.
Yeah, go on.
so just a simple question. You emphasized that coalescence was more deterministic and nucleation was more stochastic. Now, was your noise field homogeneous?
Yes, it is.
So, I mean, if you had inhomogeneous noise, would it be a fair thing to say the nucleation events will lock on to the strong noise regions?
Again, that's not something that I've looked at, so I wouldn't be able to say for certain.
Well, speculation.
Speculating, yeah. Yeah, I'm not sure you could make that kind of brushstroke assumption that it works in that way.
Well, how would you? Let's try this. What would you say about the location of nucleation events? I mean, where would you look if you didn't have your machine learning toys?
Again, a good question that I haven't thought about, but I think I'd have to think about that more before I said anything. Just because it's not a system that I've studied. I very much looked at the case where we have homogeneous isotropic forcing in a particular wave number, and that's kind of all I've had a look at. Yes.
We are all asking the same question more or less, but is it like so the forcing that do you expect it to be? I mean, because your model sort of relies on the large scales and the general features that we observe. So do you expect it to be very sensitive to details of forcing or not?
I wouldn't expect it to be sensitive to the details of the forcing, and that's purely in how if I go back to the architecture, how the system learns what the forcing should be. So essentially what we, as I say, we send in our latent variables, and we send in, this is just takes the form of Gaussian noise with mean 0, standard deviation 1. And these learnable parameters essentially modify or transform this noise into something that can inform how the output, so t+1, should look like. So as long as it's seen a data set of, again, the large scale features, but it's seen snapshots of how the system should evolve, this should be reasonably flexible to take in Gaussian noise and learn the effective transformation that takes us from Gaussian noise in physical space to the form of the forcing in physical space, as opposed to knowing anything about the prescribed forcing. We don't tell it that it's homogeneous, isotropic, forced in wave number space. It doesn't know that. It has to learn that for itself. So I assume that it wouldn't be sensitive to the forcing structure. Yeah, Richard?
So it's a slightly different question about the ability to capture the unseen, to interpolate to the unseen states. Does that rely on the underlying model having some sort of continuous dependence on beta?
Yes.
If you had a system that had a more discontinuous or some regime change, is there any chance of it picking it?
Exactly that. So again, I wouldn't be certain. It might, if you showed it data that was appropriately spread apart around these kind of discontinuities, maybe it would see that. But this assumption, this modeling approach that we took, takes the assumption that there's a continuous dependence on beta, and therefore we can pass in these reasonably coarse values of beta and then interpolate between them. But if there was, say, at beta 0.2, some sort of discontinuity, you might need to show it values at beta is 0.9 and then 0.21 for it to pick up that kind of discontinuity. Again, it's not something I'm sure about because it's not something I've seen, but that would be my approach as opposed to just giving this kind of discrete set and assuming that it can fill in the details from there.
This is speculation again, but what would be your feeling? Some models keep showing coalescence until you get to a fully merged state and you get just one massive jet or step in the system. What would be your feeling about that end state being reminiscent of the fact that you miss the small-scale nucleation, which seems to be the difficult part? So you have too simple a model for nucleation.
When you say too simple a model for the nucleation, what do you mean?
Well,
Yeah.
Along the same
Yes.
lines as, things are way too homogeneous, way too
Sure.
uniform, way too, constant in time, or
Sure, to be able to show that kind of dynamics. I suppose moving away from that, I guess less of a machine learning question, more of a dynamics question, was your question, would the machine learning be able to pick that up, or what do I think?
or given the
Yeah.
fact that you have trained and run possibly an enormous amount of such cases, whenever you introduce inhomogeneities or whenever you introduce fast variations, you get nucleations more often than not,
More often than
things like that.
Well, again, I suppose that goes down to how the system here learns. Again, it doesn't know anything about the form of the noise, and assuming that our data set had enough information in that to tell the machine learning that this is the if we have a time step t, we have time step t plus 1. These are the kind of temporal correlations that we have going between those, and in the case here, it would be that you're more likely to get a nucleation than you're more likely to get coalescence than a nucleation, or was it the other way around? More likely to get nucleation than a coalescence. If the model had seen an adequate amount of information to tell it that was the case, then I would assume that this would be flexible enough to take standard Gaussian noise and transform it appropriately, find some mapping accordingly to match what it's seen in the data. Yes.
So it seems to me, if I understood, that most of the cases you are considering have a rather high degree of symmetry.
Yes.
Almost a one-dimensional
Yes.
structure. Have you tried anything that doesn't?
Well,
In other words, say add some big vortices to your ensemble of zonal flows and stuff.
so it's not something we've looked at. What we've been looking at the moment is moving towards a multi-layer case where there isn't some prescribed forcing, but of course you still have symmetries in X and Y there. So that's not something that we've kind of looked at in kind of imposing any kind of asymmetry or kind of anything that breaks the symmetry, because you're right, that kind of reduces dynamics and allows the machine learning model to do much better than if it's got to try and work out these asymmetries. So it's not something we've looked at. But I suppose the more organic case where we're not forcing any kind of homogeneous or isotropic forcing is somewhat close to.
I had a student who played these machine learning games with it's a GFD-like plasma system called the Hasegawa-Wakatani system, which don't ask, but anyway. The point is, depending on parameters, it can behave very GFD-like in kind of 1D-like and with jets dominated and all like yours, and in the other parameter regime it goes much more to sort of a vortex state of turbulence, and his game worked very well on the first case and bombed totally on the second.
That's something that I assume would probably happen here as well, because what the machine learning model is essentially doing is it's trying to do, as I said before, it's not doing next word prediction like sentences are, but it's doing next time set prediction. It's just trying to go from one time step to the next. And it has to make a number of assumptions on how it goes from one time step to the next. And if it sees various symmetries in the system, then it tries to exploit those to give it the best chance of being able to go from one time step to the next. And by introducing additional complexity like symmetry breaking and other things there, it just makes the learning of the mapping from one time step to the next more difficult.
I mean, it presumably could train on the other limit and learn that.
It could do,
but then the real fun would be, could it pass from one to the other?
Sure. And is an interesting question, and something that I think an approach like this would be interesting, where, as you say, you train in one limit and then you give it a much smaller data set in the other limit and trying to see if it's able to move between the two, the way that we can see that this learns how to move between different values of beta, but this is, I guess, a simpler case of that.
Can you ask, in your machine learning architecture, for example, there seems to be a lot of choice.
Sure.
So is what you were using like a standard, that's what people do?
Yeah.
Or-
So I suppose that the choices came in, and I suppose if I go back to the diagram,
Yeah, this sort of
the choices come in to essentially, this is a very standard way of writing. This is almost exactly how the standard transformer is used for, whether it's used for image processing or whether it's used for natural language or whether it's used in other physical applications. The one choice that we had to make is how do we impose this value or the knowledge of this the system should be giving us that's probabilistic and therefore depends on us sampling this value of epsilon. And essentially the choice was to either include it before we have these learnable parameters, to include it after as some sort of mapping, so that the system would learn a mapping from time t to t plus 1, and then it would learn sort of a distribution on top of that, where you might look at a mean and a standard deviation, and that would be an additional layer that essentially gave you two values at the end, one for a mean, one for a standard deviation, and then you could sample that way. We chose to impose it at the beginning because we thought that we didn't want to enforce any kind of notion that the outputs of our distribution were Gaussian anyway, because as we see from the distributions, it's not Gaussian, and that's why we chose to put it in the beginning. But this is a reasonably standard architecture that's almost exact. If we got rid of this, additional value of epsilon would be completely standard to what was being done in other work. And then the other choice, I suppose, that we used was that we chose to do it with this autoencoder structure, where often some people just choose to use this middle part, but we wanted to build in this system that was able to reduce down some little latent space, evolve in the latent space and map back, just because it would give us, now that we're looking at a 2D system, we've seen that's important because 256 is fine, but 256 by 256 becomes computationally very, very difficult. And just not having the hardware to be able to do the training for that means that we had to reduce down to something more reasonable in this latent space. So those are the choices that we made. But in terms of the actual machine learning architecture, it's reasonably standard.
Coming back on this issue of continuity with beta and interpolation versus extrapolation, I mean, if the physics behave the same in terms of nucleation, merging, it just increases in numbers when you increase in beta. Would it be meaningful to, for instance, run the machine learning from one beta, small beta with only one jet, to then a larger beta with two jets, and then performing several interpolation in between those two beta, just with the machine learning, so that the system, in a sense, discovers how to go from one to two jets. And then, once the physics behave the same, then you could extrapolate towards larger beta. So this is something that you did.
It's not something we did, but it's something I sort of suppose we saw as an emergent phenomena. So I mean,
it's a kind of learning the rules.
Yeah.
Once the system knows, then if there's no bifurcation to another kind of rule, then
yeah. So I suppose what we see is that beta 0.75 for these values of epsilon and mu seem to be this kind of transitional regime where we saw these kind of latitudinal jets, these kind of sharp interfaces where we translate in one direction, and then we see this this rare event where we then move and change direction in the other in the other direction, and this was not part of, or these kind of features were not part of the kind of training data set, but we've seen that the model has learned somewhat how to go from smaller beta where we have one or two jets up to these kind of three jet system, and it's learned that these translational or these rare events in translation are seen by the system, even though it hadn't seen any of that during training. So I suppose it's almost an emergent property in the that it's learned, and it's something we're looking at the moment and diving deeper into, is to how well has it reproduced this, and what are the kind of what are the tells that it has used to be able to learn this emergent behavior? Because in the previous, oh no, I don't have it here, sorry. But yeah, in the set of training that it's seen, it hadn't seen that kind of dynamic. So it's doing something like that. But again, as you go to higher and higher values of beta, we get towards in this case, we get towards zonostrophy, and then beyond that, we get into dynamics that less, or not less similar to what we've seen, but we move into regimes where if we only change beta and don't change mu and the other parameters, that become much less physical and don't give us kind of wave-like behavior that we expect to see. And I wouldn't expect the machine learning model to be able to move up to those higher values, given that it hasn't seen anything of them.
So, can you add some layers in this model that relies on more on the physical constants like the symmetry or other stuff that can help us implement the knowledges of the physics, and on the other side, we can testify how much physics the network actually learn or actually know. Can you do those things?
So on the second question, that's something that I'm thinking about, and hopefully other people have suggestions as to in what way are we able to validate, I guess, what kind of physics has been learned. We've kind of got these evaluation metrics where we're looking at things like correlations, and we're looking at the energy spectra as one proxy of has it learned the appropriate physics. But it's definitely something I'm very interested in sort of thinking about and wanting to talk to more people about what other ways are there of validating what kind of physics has our model learned, and kind of what other ways can we scrutinize how well it has learned physics. When it came to any kind of layers we could add to impose symmetries, I guess I brushed over this because it's quite a technical diagram, but one thing we do is that we impose a latitudinal translation symmetry on the model. So when we input our time histories or our latent time histories, we take a Fourier transform, we calculate the phase of the first Fourier component, so we take the argument just by taking the arctan. We then phase align our system, so we then multiply by that value of phase, that value of phi, and that essentially means that the entirety of the system weights are calculated to be invariant to that phase, and this is because we have symmetries in y. So we don't want the model to think that if the jets are in a particular value of y, that they should be there for any other reason. So we phase align our system. We then do all the training, and we calculate the weights, and then we shift back by multiplying back by phi in Fourier space, and then take the FFT out. And that's one way that we imposed, I guess, physical symmetry knowledge to the system. And what we saw actually, and maybe I should have put a diagram for this talk because it might have been interesting to people here, is when it came to these plots, these PDFs of coalescence and nucleation, by not including that information of physical symmetry, we saw that these PDFs that it produced didn't match up to the numerics. And that meant that the machine learning had learned something, or learned some sort of superfluous, some unknown correlation between the location in Y and the jets to indicate as to how they would then evolve in time. And by having in that additional part where we take out the phase, essentially shift all the jets for one time step, calculate the time step, and then shift back, meant that the weights of the system don't have any knowledge of that Y dependence, and therefore were invariant in that way, or equivariant, because we have the shift back at the end. Does that answer your question?
well, let's just thank Ira.